Thanks to the organizer for giving me this opportunity. So yeah, my topic is this. Okay, so I want to precisely define what is the arrow of time. Okay, and for this I'll be using the Kelvin's statement of the second law, okay, which says that no process is possible whose sole result is a complete conversion of heat into work. Okay, and we'll be working with the microscopic theory. Okay, so there is no notion of heat. So what rather we will be doing is we will keep track of energy of the system. Okay. And Kelvin's statement in this fashion is that if we perturb an otherwise closed system, the system cannot lose energy. Okay. If the system lose energy, then the energy loss would have been completely converted into work. Okay. This is for positive temperature. Okay. And this statement, Kelvin's statement of the second law, we are going to call it the arrow of time. All right, and please note that we are not coupling the system to another system, and we are not quenching. Okay, we are perturbing. Okay, so we're perturbing the system momentarily. Examples are we turn on momentarily, magnetic field in a spin system, or shoot laser pulses on an electronic system. Okay, and we don't want to talk about it in terms of entropy, but if you want to talk in terms of entropy, we can use this first law. Okay, and it means that dE should have the same sign as T, so that ds is always positive, okay, when we disturb a system. But yeah, I don't want to talk in terms of entropy, okay, because I don't want to go into the details of the non-equilibrium dynamics. Okay. First, okay, since I have only 10 minutes, let me flash the result. We saw that, okay, so I'm not going to say it's a proof, okay. We motivate and we saw that quantum chaotic many-body system possess the thermodynamic arrow of time in the large system size limit. Okay. And the technical result, okay, the technical part of the result is what we are coining, we're giving the name ETS monotonicity. Okay. The F function in eigenstate thermalization hypothesis is a monotonically increasing function of E bar, okay, which gets flattened for large systems. Okay, so more details is coming. Okay. And yeah, so this is the technical part of my result. Ingredients, many-body system, okay, and I'll be using time-dependent perturbation theory, okay, this is just the first order, okay, and what we will use, since we're concerned with the, since we're talking about chaotic system, we'll be talking about various conjecture and ETS hypothesis, okay, eigenstate thermalization hypothesis, okay, and Berry's conjecture basically says that an eigenstate of a chaotic system looks like a microcanonical ensemble. I think many of the audience know this. Okay. But it was, very, stated in a different fashion. Okay, but it basically means this. Okay, so you can look up this review. Okay, for the equivalence. Okay, and since here we, in this ETH and various conjecture, people always talk about microcanonical average. Okay, so we will also need equivalence of ensembles, and of course we will be talking about eigenstate thermalization hypothesis. And yeah, I think almost everyone here knows the definition, the unjust ETH unjust. Okay, it looks like this. What is important is that F is a, I can make the complex nature. I can transfer it into this random vector Rmn, and so I can make the F to be an even function of the omega. Okay, and the omega dependence of F has been studied rigorously. Has been studied in many works. Okay. But what we found is that the E bar dependence hasn't been studied, okay, in detail, okay. And actually, our result is concerned with the E bar dependence of this F. Okay. Yeah, and as you know, the diagonal part of ETH is basically the various conjecture plus the exponentially suppressed fluctuations, exponentially suppressing the entropy. Our setup is, as I was saying in the first few slides, okay, that we will perturb the chaotic system with a Hamiltonian H0 with an operator that satisfies ETH statement. Okay, this O satisfies the ETH statement. Okay, and this H0 is a chaotic Hamiltonian. All right. And the perturbation is for a finite time duration. Okay, it's not a quench. It's not coupling a system to another system. It's just a finite time distribution, disturbance, okay, perturbation. In all systems of both theoretical and experimental interest in physics, we know that H0 and O are few body operators, okay, and for a closed system, they are also Hermitian and non-fermionic. Okay. So yeah, the crucial ingredient for this work is that we will actually enforce Berry's conjecture to change in energy when we do a perturbation, when we perturb a system. Okay. As you know, this Berry's statement and the ETH statement, it's mostly studied for observables like magnetization, occupation number. Okay. But what we want to impose this Berry's conjecture to the change in energy after a perturbation. Okay. It's because what we are basically saying is that it's hard to differentiate between an eigenstate and the corresponding thermal state, okay, observationally. Okay. So it should be equally difficult to differentiate between eigenstate and the thermal state by calculating the change in energy after a finite perturbation of the system. Okay. So this is the crucial, ideological input. Okay. And the result is not expected in a non-chaotic system. Okay. All right. Now, so I'm saying that the change in energy delta E should be same for eigenstate and thermal state. Okay. And I'm working in the leading order perturbation theory. Right? Now, the change in state, change in energy for a thermal state actually is given by this. And by the way, this the quantity inside this square bracket is called as you know, is called the spectral function. Okay. And here the lambda is the Fourier transform of this perturbation, this lambda t. Okay. And lambda t it has finite support and it is real, so it's like this. And actually this term, it comes from the first order of the perturbation theory or linear response theory, all right? And yeah, as I was saying, we have, the quantity inside this square bracket is called the spectral function, as everyone knows, okay? And it turns out that actually this quantity is always positive, okay? Or 0 or negative for positive temperature or infinite at or 0 at infinite temperature or negative at negative temperature. But note that we are working with, this is a canonical ensemble. All right. All right. While in Berry's conjecture, we have microcanonical expectation value. All right. And one thing which will later become useful, if we do a Taylor expansion in terms of omega, what we will find is that this in the Taylor expansion of this, there will be only even powers of omega times f squared. All right. And so for now, since this quantity is positive, and we are saying that in the eigenstate, this quantity should be same as the thermal value. Okay. So Berry's conjecture applied to the change in energy, and using the equivalence of ensemble implied that the quantum chaotic system possesses the arrow of time in the large system size limit. Right. And this is true for typical states, okay, with non-extensive variance of the energy. Okay. I won't go into this typical pure states, okay, but because of the lack of time, but it can be done very easily. Right. And so, yeah, so I'm plotting for a chaotic XXZ spin chain. Okay, this is the density of the state plots. Okay, and yeah, so we have positive temperature here, negative temperature here. Okay, and yeah, and the change in energy is always positive for positive temperature, negative for negative temperature, and 0 for around temperature infinity. Okay, and it's not happening for non-chaotic XXZ spin chain. Okay, and comes the technical result. Okay, so yeah, the technical result is that if we calculate this change in energy in the eigenstate, okay, it looks like this, and if I substitute ETH and just in this, okay, what happens is that all powers of omega times f squared arises. Okay. But as if you remember here, only even power of omega arises, okay? So it implies that in the large system size limit, when we have equivalence of ensemble, the f is a flat function. All right. And actually we can argue, okay, so my this work has analytic motivation, and I'm illustrating it with numerical results, okay? So it's not just a numerical exercise, okay? And so it implies that the f flattens for large systems, okay? And yeah, so and we can show that f is a monotonically increasing function for finite system, okay, as a function of the magnitude of the effective temperature T for E bar, okay, and this numerical plot supports it, okay, and the flattening of the the flattening of the f, okay, I'm trying to tease it out here, okay, and I can actually this is the numerical result. I can show that actually the flattening happens as L inverse, okay, L to the power -1, okay, it flattens like this, okay, as the system size grows. Okay, so yeah, conclusion, we saw that the quantum chaotic many-body system possesses the thermodynamic arrow of time in the large system size limit and at leading order in perturbation theory. Okay, it follows from Bayes' conjecture and the equivalence of ensemble. And we found a new property of quantum chaotic system, which is we are coining it as ETH monotonicity. That F is an eigenstate the F function in the eigenstate thermalization hypothesis is a monotonically increasing function of the magnitude of the effective temperature of E bar. Okay. And this quantity flattens as L inverse. All right. And this term, it was suggested by the referee, and it's right now under review here. Okay, and since it's a new property for quantum chaotic system, actually we have many follow-up work in line. Okay. And actually, this ETS monotonicity, it can also be considered as a quantum advantage. Okay, because it basically means that quantum chaotic system wants to absorb more energy. Okay, all right, more chaotic system absorbs more energy. All right. So it's actually, if you build a battery out of more quantum chaotic system, actually it means that you can charge the battery faster. So it's just an advertisement, but it can be talked in terms as a quantum advantage. Okay. So I'll stop here.
One quick question.
Actually missed the result parts. What kind of model, the numerical results are shown for what setup?
Oh, it's XXG spin chain with next to nearest neighbor. But as I was saying, okay, I have analytic motivation or proof. Okay.
So it was XXG with next nearest neighbor.
Yeah, next nearest neighbor. Yeah.
Okay, so let's thank our speaker.
Thank you.